Hello friends, welcome to the class of High Voltage Engineering. In previous lecture, I have discussed the Hall effect generators. The Hall effect generators are not only used to measure the high direct currents, but they can also use to measure the post arc currents as well as the unidirectional impulse current. In today's lecture, I am going to discuss the Rogowski coil or the magnetic potentiometers and the Faraday generator or Faraday ammeters, which are used to measure the high frequency alternating currents, impulse current and other rapidly changing current in high voltage laboratories during the research practices or even at the power system sites. So let us start with the Rogowski coil. So Rogowski coil is known as a magnetic potentiometer which is used for the impulse current measurement. So my friends, you have already used the clip-on meter. You know the operating principle of clip-on meter and how it works. So clamp meter or the clip-on meter works on the principle of Faraday's law of electromagnetic induction. To measure the current with the help of clip-on meter, it needs the either alternating current or the currents which are rapidly changing. Okay, so alteration is of course required when we want to measure the current by using the clip-on meter. So when the current is passing through the conductor, ultimately what we are doing, we are clipping or we are clamping the one side of the meter surrounding the current carrying conductor. So when the current carrying conductor is passing through the conductor which is alternating in nature, according to the Faraday's law of electromagnetic induction, the EMF is induced, and that EMF in turn gives the indication in terms of the magnitude of current which is flowing through the conductor. The same concept, same operating principle is also being used with these magnetic potentiometers. So here you can see that there is a one current carrying conductor, okay, which is wrapped by this coil. This is the Rogowski coil. So ultimately, as you can see over here, that the one coil is surrounding the current carrying conductor. So obviously there is a mutual induction between the coil of this magnetic potentiometer and the current which is being flowing through the conductor. So you know the Oersted statement, when the current is flowing through the conductor, the magnetic field is produced. Now as the current is rapidly changing or alternating in nature, so magnetic flux which is being linked with the coil is also changing. As a result, there is a self induction. So EMF is induced, and that EMF is denoted by this VI of T. Okay, because ultimately we are getting the alternating voltage. Okay, so VI of T is given by this formula, which is M into DI of T by dt, where DI of T by dt represents the rate of change of current. Okay, so this rate of change of current will induces the voltage, but that voltage is somewhat very less, which we cannot measure directly with the help of our ordinary instrumentation. So in that case, what it needs the integrating network. Okay, so by having the integration, we can have the detectable output at the output circuitry of this Rogowski coil. Okay, so this is the basic circuit diagram of the Rogowski coil. So if the coil is placed surrounding the current carrying conductor, the voltage signal is being induced, and that is given by this formula, where M represents the mutual induction. So ultimately this M will plays very important role. So to have the proper signal output, there must be the tight coupling So to obtain the tight coupling, the coil of this magnetic potentiometer will wound up very close to the current carrying conductor, so that we can avoid the magnetic isolation between the current carrying conductor and the Rogowski coil inductive coil. Okay, so tight coupling concept need to be considered, because when we are wrapping the coil surrounding the current carrying conductor, the air is present. Okay, so we can one can consider this is a one type of the air core kind of the structure, so that we can avoid the saturation problem which we can see in the iron core type of uh, uh, current measuring device like the current transformer. So we cannot we cannot prefer to measure the rapidly changing current with very high frequency range by means of this current transformer, because they always prone to the they always subjected to this saturation, and once the saturation takes place, it may introduces the harmonics. So it is very bad while we are measuring the high value of the currents which are rapidly changing, like the impulse currents with the CTs. Okay, so the problems can be eliminated by having the non-contact type device, where we can avoid the physical connection of the current carrying conductor with respect to the metering equipment and the person who is handling this instrument to measure the impulsive currents. Okay, so as the air is acting between the current carrying conductor and the Rogowski coil, the tight coupling is required just to avoid the magnetic isolation. So you need to wrap the Rogowski coil very close to the current carrying conductor just to avoid the magnetic losses. So the coil is usually wound on the non-magnetic former of toroidal shape, and is coaxially placed surrounding the current carrying conductor, as you can see in the photograph or the picture or the circuit. So number of turns on the coil is chosen to be large, just to get the enough signal to be induced so that we can get the detectable output. The coil is wound crosswise, as you can see over here. It is wound up crosswise just to reduce the leakage inductance, and the integrated circuit is employed to get the output signal voltage which is proportional to the current, which is our prime requirement. Okay, so ultimately here Vi of t, that is the induced voltage, and once we are considering this integrating circuit, then it is given as Vi of t is equal to 1 upon Cr or Rc integrating integrating 0 to t V of t. Okay, here one can measured output Vm of t. Vm of t is equal to 1 upon Rc integral 0 to t Vi of t. That is the voltage that we are being measured. We are going to measure at the output terminals of integrated circuitry associated with the magnetic potentiometer. So Vm of t is equal to 1 upon Rc integral 0 to t Vi of t dt, which gives M upon Cr or M upon Rc into I of t. Okay, so here you can see that the Vm of t is now proportional to this I of t. So Rogowski coil with electronic or active integrator circuit have large bandwidth about 100 MHz. At frequencies greater than 100 MHz, the response is affected by the skin effect, the capacitance distributed per unit length along the coil, and due to the electromagnetic interferences. However, the miniature probes having nanosecond response time are made using very few turns of copper strips for ultra high frequency measurements. So let us see the concept of the Rogowski coil.
A Rogowski coil is a device for measuring AC electrical current. The coil is a helical winding of wire, resembling a large spring, with one end of the wire passed back through the center of the coil. When the coil is wrapped around a conductor through which current is flowing, voltage directly proportional to the current is induced in the coil. The AEMC Amflex and Miniflex families of AC current probes incorporate Rogowski coils. Some of these probes include electronics to provide a stronger and linearized output signal. The diagram on the screen illustrates how these probes function. In this diagram, the probe's Rogowski coil has been placed around a conductor. As current flows through the conductor, it induces a voltage, called V1, within the coil. V1 varies in proportion to two values, the amount of current in the conductor and the AC frequency of the current. Calculating current from V1 requires the formula shown on the screen. In this formula, K is a value derived from the physical characteristics of the coil. These include loop size, the number of turns, and the length of the winding. dI/dt represents the change in current over time. This is dependent on the current's frequency. To convert V1 to a linear, frequency-independent output voltage called V2, the probe's electronics remove the time frequency variable from the equation. To do this, the electronics automatically adjust the gain in accordance with the current's frequency, using the formula shown on the screen. In this formula, Kf is a value derived from the physical characteristics of the coil for a given frequency. V2 can then be used to calculate the associated current by applying a frequency-independent scale factor, such as 1 millivolt equals 1 amp. For example, the probe can be connected to a digital multimeter or other measurement instrument to calculate and display the current reading based on the input voltage and scale factor. Rogowski coils offer several advantages over other probe types such as ion core, Hall effect, and flux gate. For example, they provide high resistance to electromagnetic interference, and there is no saturation when measuring high currents, ensuring the probes are subject to very little heating. They are lightweight and flexible. The probes can be wrapped multiple times around a conductor to amplify sensitivity, and they can be left unterminated without being damaged or developing hazardous voltage levels. The AEMC Amflex and Miniflex families of AC current probes enable measurements on conductors where standard clamp-on probes cannot be used. Amflex and Miniflex probes are lightweight and can be installed in tight places, around cable bundles, around wide or large bus bars, or even wrapped around irregular shapes. These probes create virtually no load on the system under test, have a low phase shift and excellent frequency response, and cannot be damaged by overloads. And they are insensitive to DC currents, so only the AC component of the measured signal is displayed. These probes produce a millivolt output, proportional to the current measured, for direct readings on digital multimeters, loggers, and power meters. Models specifically designed with a 1 MHz bandwidth are ideal for oscilloscopes, and the probes come in a variety of lengths. Amflex and Miniflex probes can be used in a wide range of applications, including power measurements, measurements on switchboards and thyristors, switching measurements, and display of control signals. This concludes our brief review of how Rogowski coils function and the advantages they provide. For more information about Amflex and Miniflex probes, visit the AEMC website, and be sure to check our YouTube channel for instructional videos about other topics in electronics.
Okay, so in video that you have understand that the Rogowski coils are insensitive towards the DC component of the fault current, because the DC produce the constant magnetic field, and to have the satisfactory satisfactory performance with this magnetic potentiometer or Rogowski coil, it needs the alternating magnetic field, okay, or rapidly changing magnetic field. So DC will not support to this change in magnetic field, so ultimately we cannot have any kind of output. So this Rogowski coil can measure the AC component of the fault current, as it supports to the production of the changing magnetic field on which the Rogowski coil works. So let us discuss the difference between the bushing type CT and the Rogowski coil, or electromagnetic current transformer versus Rogowski coil. So one can derive so many differences by just looking to the uh, design of both the equipments. So characteristic, first is the metering. So bushing type CT, the two CTs are used, one for metering and one for protection. Whereas in case of Rogowski coil, the one coil is used for both the purposes. So that is the advantage. Saturation characteristics. So for the symmetric currents, the saturation starts near 20 times rated current and rated burden in case of bushing type of CT. Whereas for asymmetric current, the saturation can start at several times rated current depending on the primary system X/R ratio. In case of Rogowski coil, no saturation, okay, because the magnetic core is not present. Okay, here normally the non-magnetic material is used to form the or to done the winding. Okay, so the insulating former is used. Okay, so non-magnetic material is there, so there is no problem of saturation. So it has a better linear characteristic between the output and input. The high frequency range, bushing type CT typically up to 50 kilohertz, whereas Rogowski coil up to 1 megahertz or greater. Remanence, the remanence is possible in case of bushing type of CT. Here, as there is no iron core, so there is no remanence. Secondary wiring, in case of bushing type CT, it requires heavy gauge conductors with shorting type terminal blocks, whereas in Rogowski coil, shielded twisted pair cable with no connector. Okay, so no sorting blocks are required. Size and weight, okay, it is large and heavy, whereas the Rogowski coil is very small in construction and lighter in weight. Differential protection scheme, for case of this bushing type of CT, it needs several CTs with different voltage current characteristic, okay, to cover the multiple protection schemes. Whereas in Rogowski coil, only one RC circuit can be used for the for enabling the multiple protection schemes. Personal safety, as you know that the electromagnetic CT can never be operated under open circuit conditions, because the open secondary can generate the high dangerous voltages. Rogowski coil, it provides the isolation, so it is very safe to operate even under the open secondary voltage is too much small. Okay, under the open circuit condition, because in that case the open secondary voltage is too much small, so it is safe to handle. The impact of environment, the electromagnetic CT normally use the oil as insulation. So oil insulated CTs, the oil can be leak out and may rupture the CT. SF6, if you are using it, then the insulated CT, there may be the problem of gas leaking. In case of Rogowski coil, no oil, no SF6 gas, so it is environmentally friendly and very safe. So this is about the some kind of the differences between the electromagnetic current transformer and the Rogowski coil. Now the Faraday generator or the emitter. So this method is also known as a magneto-optical method and usually used to measure the current in terms of kiloamperes, which one can assumed when there is a situation of the lightning strokes and all. So here there is a total isolation observed between the person who is handling this device with respect to the current which is being flowing through the current carrying conductor. So Faraday generator or the emitters normally works on a very simple operating principle. So as you can see over here, one light source is there. Okay, so from this light source, when a linearly polarized light beam is passing through this crystal, okay, so generally the crystal will surround the current carrying conductor. So when we are passing the light beam, then the light beam will passes through this transparent crystal in the presence of magnetic field, because when the current is flowing through the conductor, the magnetic field is produced. Okay, so here the light beam is passing through a transparent crystal in the presence of magnetic field. So the plane or the polarization of light beam undergoes the rotation. As you can see over here, there is a reflection and the refraction of the light wave which is passing through this crystal which surrounds the current carrying conductor. Okay, so this situation will happens when the magnetic interaction will be there. Okay, so the angle of rotation alpha is given as V into B into L, where V represents a constant of the crystal which depends upon the wavelength of the light, B represents magnetic flux density, and L represents the length of the crystal. So to measure the waveform of large current in extra high voltage system, this kind of arrangement is normally used. So beam of the light from a stabilized light source is passed through a polarizer P1, because we need a polarized beam. Okay, so to achieve this polarized beam, first the light beam is passing through this polarizer P1. Okay, and then it will be fall on this crystal F, which is placed parallel to the magnetic field, produced by the current when it is flowing through this conductor. So now as there is an interaction of this magnetic field with respect to the polarized beam which is passing in this crystal, it will goes under the rotation. So the light beam undergoes a rotation of its plane of the polarization. So this will represent the rotation of this light beam when there is an interaction of the magnetic field. So after passing through this analyzer P2, the beam is focused onto this photomultiplier M. The function of this photomultiplier is to convert the light into the electrical output signal. So the output of this photomultiplier is fed into the CRO for the analysis purpose. Okay, this is the photomultiplier C, sorry, not the M. M is a filter. Actually it is filter. Okay, so particular range of frequency of the light is only being applied to the photomultiplier for the conversion from light into the electrical output signal. Okay, so this filter M only allows monochromatic light. The relation between the oscillograph display and the current to be measured are very complex, but it can be easily interpreted. The advantage of this method are there is no electrical connection between the source and the device. As you can see, the CRO or the person who is handling the device is at the ground and the crystal is mounted onto the transmission line conductor. So there is no physical connection. There is a complete isolation. So as there is complete isolation, there is no thermal problem even for a large current of several kiloamperes. and as the signal transmission is through an optical system, no insulation problems or difficulty arises for the extra high voltage signal. Okay, only the drawback is that this device never operated under the DC current. So this is about the Faraday generators or the Faraday emitters, highly applicable for measuring the current of several kiloamperes isolately. Thank you.